A slightly different example for ABE. Some of you have seen this before, but I promise there's a small twist at the end. So think about trying to do ABE for, there's this mandatory mentioning that I need to say big data somewhere during this workshop. So think about trying to do sort of using ABE for solving some kind of dating meets big data. All right? So you have a user who wants to date on the internet, and you want to publish. The user wants to publish some sort of a dating profile. So the dating profile contains all kinds of personal information, pictures, email addresses, age, hobbies, blah blah blah. And you really want to limit access to this profile to people who fit your dating criterion, for instance. So what you want to do is essentially what AB allows you to do is to encrypt the profile, and it does, in addition, specify access policy. Think of this as specifying like a dating preference, something very mundane like tall, dark, and handsome. But of course, we're among friends here, and people who know better. Really, in the Bay Area, what you want is to look for someone with a PhD in computer science. Right? So so AB allows you to specify a policy like this. Think of this as the attribute. Earlier, we talked about attribute being a string X, but when we have AB for circuits, you can also encrypt to a circuit also, okay? So users come along, they register for their website. You have different users. When they register, they maybe present their diploma to the dating website, and then they get keys that are customized to the kind of characteristics that they have, right? So in this particular case, I'll be able to decrypt the profile, and I found true love on the internet. But then, for the people who do not satisfy this policy over here, they should not be able to decrypt the profile. Right, this is what ABE says. Moreover, ABE guarantees security against collusion. So even if all these people come together, you have a collusion, they still cannot learn anything about the profile. Right? So this is where sort of the story of ABE ends. The trouble with using ABE is that ABE doesn't protect the dating preference. It doesn't protect the attributes. And one can imagine many scenarios where, not only is your profile sensitive, you can think of many scenarios where your dating preference is so sensitive that you do not want to reveal to people, right? Except maybe for those who already match your dating preferences. So you want these people to still not be able to learn anything about your dating preferences. You want to protect the privacy of your attribute. All right. So this is what we'll be talking about. So earlier we have already seen attribute-based encryption. So the community has put forth stronger notions of encryption, that namely predicate and functional encryption, that are like ABE, but that in addition provide some privacy guarantee for the attribute. All right. Let me try to tell you what these objects are. So let me start with the syntax of these attributes. All right. So all of attribute-based encryption, predicate encryption, and functional encryption, they have the same syntax and the same correctness guarantees. So there's an encryption algorithm that takes its input a public key, an attribute X and a message, and produces a ciphertext. Okay. In addition, you can create keys for predicates. All right. And the basic syntax and correctness requirement is that if you have a key for which the predicate equals to true on X, you can decrypt and recover the message M. And you have a key for which the predicate equals to false. When you try to decrypt, you get perp. All right. So in some sense, the keys do tell you whether P of X is true or false. That's in some sense inevitable. All right. Then the next question, what are the security guarantees? In ABE, this is sort of the weakest, followed by stronger and stronger. There's no security guarantee regarding the X, only to M. Right? In all of them, they are going to have the guarantee that if you have a key for which the predicate is false, you should not learn anything about the message M. Okay. So in the case of ABE, since we never have any security guarantee pertaining to X, we can essentially in ABE essentially always publish X in the clear. And that's really what all the schemes are doing. Predicate encryption provides slightly stronger guarantee. It hides X. So if you have a key for which the predicate is false, it hides X. Okay? So think of it in the context of dating as, everyone who do not satisfy your dating profile do not see the rainbow flag. And that sort of makes sense. If they can decrypt your profile, in some sense, there's probably other clues for which that might reveal information about X already. Okay, so this is sort of the intermediate security requirements. Functional encryption provides a stronger security requirement, security guarantee. Namely that in the case where the predicate is false, it hides both the X, the attribute, and the message M. And in the case that the predicate is true, here you cannot hope to hide M anymore, but you still hide X. All right. Let me say that by hiding X, you cannot hope to hide X completely. You will reveal P of X. What I mean was you hide X, everything about X beyond the fact that P of X equals to true or false. All right. So some of you may be more familiar with a definition of functional encryption that doesn't talk about message. This is essentially equivalent. There's a transformation to go between one to the other. All right. So right. So.
Sorry, I just don't understand annotation. You're talking about what the ciphertext hides even from the owner of the key, or what the ciphertext hides from somebody who knows the public key?
From the given someone who holds the secret key and the ciphertext, you still hide X.
Okay, so
in this particular setting, think of this as a guarantee for one key and one ciphertext for now. Right? In fact, this is for the simplified setting where there's only one key, but security guarantee also holds amongst collusions. Right? So in particular, if you're in this column over here and you collect many keys for which the predicate is false, you still should not learn X. Okay. So, right, so the formal security definition can be essentially the same as the one for ABE. They extend naturally to the setting for hiding X. All right, so I'm not going to say precisely what the, I'm not going to present the exact security game. Right, so this is roughly the differences there. And the main open problem in the study of functional encryption is whether we can construct functional encryption schemes for all circuits. Right? So what we've seen from Vinod's talk is that we do know how to construct attribute-based encryption for all circuits under LWE, and really we want to get to functional encryption, which is the hardest one. But even before we get to functional encryption, the natural question is, can we even get to predicate encryption for all circuits? So let me quickly, and the answer sort of is sort of yes, and I'm going to give you a quick summary of prior works. So this is sort of a summary of prior works. So there are the white regions and the gray regions. At a high level, the white regions corresponds to the classes for which we have constructions under standard, well understood assumptions, and the gray region corresponds to for constructions under less well understood assumptions. Right. Let me say this a little bit more. So like Vinod said earlier, we do have attribute-based encryption for circuits. And we can get them, this is this region over here. So ABE is a subclass of functional encryption. So with ABE for all circuits, and we know how to do this under standard LW assumption. All right. Moving up a little bit more, we know how to get predicate and functional encryption, but only for very simple functions. Functions that are contained within NC1, even much simpler than that. So functions that essentially compute an inner product, plus a variant of an inner product, like threshold of an inner product, or something like that. Think of it as you can essentially only do it for simple, for inner product. So this is a very small class of functions. And in this case, we actually have constructions both from the standard LWE assumption, and we have construction based on pairings, so bilinear maps, standard assumptions over bilinear maps. All right. So that's sort of region 1 and 2. That's all that we know essentially from standard assumptions. And finally, we do know functional encryption. We do have candidate constructions for functional encryption for all circuits. However, they rely on fairly strong and not so well understood assumptions like obfuscation and multilinear maps. Right. And if you were here at the previous workshop, if you really look at the status of these assumptions, you realize that the status is somewhat complicated. Okay? So we really want to avoid complicated situations. And as Elon would say, real cryptographers don't use obfuscation. We're going to try to avoid, we're going to really try to focus on how far we can go while relying only on standard assumptions. LWE or pairing type of stuff. Sorry? Roseanne 14. There's a link on Facebook to a PowerPoint slide to and so on and so forth.
Wait, so are you saying that this whole morning we need to wait have a site to Facebook? Like that's the...
Yeah. It's all about Facebook. It's all about social media and right. So.
There was an addendum to this code. There was a second part to this code, which is real cryptographers use build one-way functions.
I see. Right. We built more. Right? So we're cryptographers. We're going to. So the main result for this talk is we solved the next open problem. We made serious progress towards trying to get functional encryption for all circuits. We get predicate encryption for all circuits under standard sub-exponential LW assumption. Right? So the assumption here is basically the same one that Vinod presented for ABE for circuits. All right. Going back to the picture, basically we enlarge this white region over here to this much bigger white region over here. This is sort of what predicate encryption is. Okay. So there's still a little bit that we didn't quite catch, but this is the best we can do in some sense. This is the best we know how to do from LWE at this moment. Right, let me say a bit about the parameters of schemes. So we get short ciphertext and short keys. The parameters are essentially inherited from the ABE schemes. Right? So we have short ciphertext whose size depends polynomially in the bit length of the attribute X, on the depth of the circuit, and on the security parameter. All right, the keys also have this very nice property. And in fact, not only are the short ciphertext short, the encryption algorithm also runs in time polynomial in these parameters. So this is a notion of compactness, which is something that people have been using lately to build more complex primitives, which I'll talk about later in the talk.
So this is the same parameter that in the nodes?
Sorry?
This is the same as in the nodes?
Yeah, the same parameter, the same qualitative and quantitative dependency as in Vidal's talk. So the same, this is a levered construction. All right, so I want to tell you what our construction looks like. Yeah.
The reason you don't get quite two, because you don't get functional encryption?
Yeah, we get predicate encryption, which is the sort of the slightly weaker one-sided notion. We only protect X if you get keys that cannot decrypt the ciphertext. You only get keys for which P of X is false. But this is already big progress, you know. We're almost there. We went from here to here, you know, so we'll get there. Yeah? And I'll go back to functional encryption later also. Yeah? So here's a quick recap. So the starting point of our construction is the ABE scheme that Vinod talked about. So we think of ABE as an encryption algorithm that takes a public index X and a message M and outputs a ciphertext with respect to some public key. All right. As Vinod explained, the BGG plus ABE has the property that has some sort of a recoding property, namely that given an encryption for the attribute X, together with X in the clear and some predicate in the clear, you can turn it into an encryption of the attribute P of X. Right? So you start out with an encryption, just focus on the attribute part. You start out with the attribute being X, you can turn the attribute into P of X by sort of performing public operations on the ciphertext. But there's a switch here. This encryption is no longer respect to the same public key from before. It's going to be a public key that depends on P. All right? Then once you get here, the secret key essentially is if you want to decrypt when P of X is 0, that's our notion of true, you basically sort of create a key corresponding to this particular public key and the evaluation being 0. That's basically what Vinod was saying. Okay? So this is our starting point. All right, this is our ABE scheme that we will be using, and this is sort of the, roughly speaking, essentially the only property that we need from the ABE scheme for now. Right. So the starting point of our construction starts off with this idea of Go-Buster et al. Namely, oh, sorry.
Can you go back?
Yes, of course.
So you're computing already the policy on X?
Yes. During decryption, so the encryption, this is the actual ciphertext. The decryption works in these 3 steps. So given the policy and the X, you compute encryption of P of X, then you decrypt this value. So there's some sort of a homomorphic evaluation going on during decryption. This is basically the same operation that Vinod was talking about.
So essentially you can summarize what you do as the same as Vinod, but just you hide the input in case the...
Sorry, no, sorry. This is just a recap of what Vinod talked about. I haven't said what our construction is. Just to make sure that we have the same interface. All right, any questions? All right, now I can tell you what our construction is. Yeah? The starting point of our construction is the construction of Go-Buster et al. What are we trying to do, right? We want to protect X. Okay? So the natural thing to do is to first encrypt X using a FHE scheme. So we want to sort of protect X while enabling some sort of computation on X. So the natural thing to do in some sense is to first encrypt X using a fully homomorphic encryption scheme. All right. For the construction, it suffices to use a symmetric key fully homomorphic encryption scheme. So I'm going to denote this as this is a fully homomorphic encryption of X under the key K. Okay. So think about the encryption algorithm as follows. The first thing you do is on input X, pick a random key K, encrypt X under K, and treat this as the new attribute. Okay. And then run your original BGG plus ABE and with this as your new attribute. Okay. Now, if you look at this, there's some sense in which X is already hidden because X is protected by the FHE. All right. So for the next couple of slides, let's ignore the issue of security for now and think about correctness. How do we decrypt? Right? How can we decrypt without knowing X?
Does the policy have to know K, or
Sorry?
is the policy a function of K too, or something now?
No, this is just a ciphertext. Yeah, I'm going to tell you. Oh, right, this is just a ciphertext. Okay. So how do you decrypt? You get a key for, you get the P and the secret key for P, then you try to do something. Okay, this is just a ciphertext.
So now only encryptor knows K, right? Only encryptor knows K.
Encryptor knows K. Encryptor picks a random K, a FHE secret key during encryption, encrypts X under K, treat this as the attribute, and then run the ABE. Any questions what the construction is? Well, let's think about what decryption might look like. So I'm also going to, as part of the ciphertext, this is a ciphertext for our new encryption scheme. As part of the ciphertext, I will also publish the FHE encryption of X. That's okay because X is already protected under the FHE. This is not going to affect, intuitively, it won't affect security of X, the privacy of X. All right. So now what do we know? Now the decryptor is going to see this together with this. Okay? It's going to get a P and potentially some secret key for P, but it's going to get P for now. Right? Now what we know is that since this is a fully homomorphic encryption scheme, if I have this ciphertext, I can compute an encryption of P of X. Right? So this operation of computing an encryption of P of X from the encryption of X is some public operation on the attribute. Right? So we can apply this public operation on this attribute, run the ABE operations, and turn this into an encryption under the attribute, which corresponds to an encryption of P of X.
But here, why do you need FHE encryption of X? You just need the public key for the FHE. Oh, actually, there is no.
No, you need this. Well, using the fact that from an encryption of X, you can go to an encryption of P of X. And this is a public operation. So this is a public operation. There's a public operation that goes from this to this.
Wait, so why do you, I thought you already had
Yeah, you
that
have
in the ciphertext. Why do you then need to add it in?
Wait, sorry. This is the attribute. All right.
Yeah.
I'm going to assume that your ABE ciphertext doesn't contain the attribute. It's important here.
Oh,
So
that's, oh, I see. So you need, okay, that's why.
So I'm going to separately give you the FHE
So you
ciphertext.
give it as input to the encryption function, but it's not part of the ciphertext. That's why it needs to be somehow.
Yeah, we'll provide that as well. So the output here, think of it as S times some matrix type thing. That's only the only part. Okay? So we separately also give you the FHE encryption. Okay, this is sort of the ciphertext we work with so far. Now there's some operation that goes from here to here. And when there's some public operation going from here to here, our BGG plus ABE scheme then guarantees that you can turn this attribute over here to this attribute over here.
So your operation is going to be FHE eval of P?
Yes, exactly, yeah. The operation we compute is FHE eval of P on the encryption of X. Okay? This is the operation on the attributes. Then your ABE algorithm tells you a different algorithm to evaluate this particular algorithm on the ciphertext. So you get to this over here. Any questions so far? All right. So,
You guys have to generate the secret key for this.
sorry, I haven't talked about how to generate the secret key, yeah. But really, now we want to talk about generating a secret key. In some sense, at this point in time, sort of we do not know X, we don't know K. So in some sense, from the decryptor's point of view, it seems very hard to decrypt this thing because you really, since you don't know anything about K, you essentially don't know anything about X. Right? So in some sense, so now we are faced with a conundrum over here. Right? We want to somehow release a little bit of information about K in our new ciphertext, right? So that you can, check whether P of X is 0. And yet at the same time, we want to protect K, because if we completely give up K, you will violate security. Right? You no longer have security from the, you no longer can use semantic security of the FHE scheme. Right? At the same time, we need to give up a little bit of information about K so that you can check whether P of X is 0. All right? And this is actually a very hard problem, because what roughly we need to do is essentially we need to give up a way for you to test whether P of X is 0 without decrypting X itself. All right? And for those of you who know the existing candidates or approaches to building multilinear maps, this is as though I want to give you a 0 testing parameter for the predicate P that doesn't somehow completely violate security and allows you to solve discrete law. Right? These are the kind of things that exactly what makes 0 testing hard. Okay? And yet we're going to show how to solve this problem while relying only on the LW assumption. Okay. The second difficulty, if you think about it, is that it looks as if we haven't accomplished anything. Why? There's something circular about the whole reasoning, right? So our goal is to protect X while being able to enable some sort of computation on attribute X. Right? Now I'm trying to say I want to protect K while enabling some sort of computation on K. So how is this different from trying to protect and compute on X from scratch?
Well, for K, you know that how it was chosen. You chose it yourself.
Right, so that's one part of it. So you know the distribution of K. More importantly, you know the computation on K. Right? Now the computation on K is FHE decryption. Right? So what we want to do is sort of use K to decrypt this FHE ciphertext. Right? So this is, and the ciphertext is something that you can also compute yourself. Given the encryption of P of X is something that you can compute yourself also. So really, the whole key.
Using what? You can compute what? Sorry.
Oh, you can compute the FHE encryption of P of X. Given FHE encryption of X. Okay. So really, the only magic, really the thing that you're trying to compute on and keep private is the FHE secret key. Right. And FHE decryption, the key observation here is that FHE decryption is a very simple function with respect to the FHE secret key. Right. So yeah, it's trying to protect a very simple computation on the key K. And in fact, FHE decryption corresponds to essentially just computing an inner product. And we know predicate encryption and functional encryption schemes for computing an inner product. Right. So really, we're crucially using the fact that this is a very simple computation on K.
This is very specific to LWE. It's not like, I think, the previous paper of Shafi et al. Where there was a generic thing with...
Right, yeah.
This is like really specific to LWE.
Yes. Okay. So really, we crucially use the fact that it's a very simple function as a function of K. All right. So since we have predicate encryption and functional encryption for simple functions, now we can say, let's embed this K as an attribute. Okay. And since we're only doing simple computations, we can hope to protect this attribute. Okay. So here's our final ciphertext. Okay, here's our encryption algorithm. You get input X, you pick a random key K. Okay, then you compute FHE encryption of K. Okay? And you treat the concatenation of K and the FHE encryption as your new attribute. So now your new attribute has two parts: an FHE secret key and the FHE ciphertext. Okay, and then you output whatever the ABE encryption outputs. And then you output the FHE ciphertext part, and you don't output the K. All right? So that's the entire ciphertext. So there's an ABE encryption with respect to some attribute that contains the FHE secret key and FHE ciphertext, and you publish the FHE ciphertext, but you don't publish the K.
So sorry, I thought that for ABE, it was without also generality that the ciphertext contains the attributes. You're assuming that there exists ABE where it's not the case? Or?
We usually, in ABE schemes, when you give out something, you get S transpose A1 plus X1. You can just, usually you separately tag on the X. So ignore whatever part that tags on. Don't tag on the X. So the ABE construction outputs some LWE sample, just keep those LWE samples.
So again, you're using a specific ABE scheme as opposed to...
Yes. This is not a general... Yes, we'll be using the BGG plus ABE scheme. Any questions? Yeah.
Yeah. The previous talk, didn't you need to know X to be able to compute this ABE?
To decrypt.
To only, not even to.
You.
Create the encryption. I thought
No, to encrypt you know X. To decrypt you need to know X also in the previous scheme.
To evaluate on the encryption.
Right. You need to know X. Yeah. So I haven't taught you how to decrypt yet. So you don't know K here. That's a great question. Yeah. So this is the ciphertext. I haven't taught you how to decrypt yet. Okay? And in fact, with this ciphertext, you cannot even run the previous ABE decryption algorithm because the previous ABE decryption algorithm needs to know the entire attribute in the clear. Okay? So like I said, let's focus on trying to do decryption. Okay? So let's see how to decrypt. Right? So first of all, we can still compute on this part. Okay? Because we know the FHE encryption, the ciphertext contains the FHE encryption of X. Okay? So we can still, as before, compute on this part.
So here you're just using the fact that the ABE scheme treated the bits sort of separate.
Right, yeah, exactly, yes. So we can compute on this part and we get this thing over here. Right? Now that's the hard part now, right? So what we really want to know now to be able to do is to use this K to decrypt this ciphertext. right? Which essentially corresponds to just computing an inner product. Let's pretend for now that FHE decryption is just computing an inner product. Right? So what we want to do is to somehow take this and this over here and compute the inner product without knowing what K is. Now we are going to crucially use the fact that this inner product is a very simple function. Right? Let me say that if you can compute the inner product, this is basically the FHE decryption of this ciphertext, then you get P of X over here, then you can proceed as before. So now the question, the magic is...
Problem with the noise, and you're not really getting...
the noise, you can solve it. You can solve it for the same reason, you can solve it.
The noise would destroy linearity. You can't... you can live with the noise.
So let's just assume FHE, exactly. The short answer is yes, but let's assume for now that FHE decryption is exactly inner product. Okay, that will come up when talking about decryption. All right. So let me tell you how to go from here to here. Okay. Yes.
You're saying at the end you have AB encryption where the label is P of X?
It's the inner product of K together with this. And this is basically a decryption of this FHE ciphertext over here. So the decryption of this FHE ciphertext is essentially P of X here. The P of X is actually a number, and all of the existing construction, you don't have to work with S1 being bits. If X1 is a number, it's just fine.
So, isn't it true that what you showed here actually shows that given ABE, you can go to predicate encryption just by designing a predicate encryption for the decryption circuit of FHE?
Yeah, you're way ahead, yeah.
But this is it. So there is a general theorem here.
Wait, that's a slightly orthogonal issue for now. This is the question of relation to prior work, right? So maybe I'll take that offline.
Why doesn't this give you a functional encryption?
Great question also, but let me finish correctness of the algorithm. Okay. Are there any questions for now? Let me explain correctness. We're going to, roughly speaking, we're going to look at how the previous homomorphic algorithm works. Turns out we need to do inner product, which is the sum of products. So we just need to focus on, turns out the addition is the easy part. The hard part is doing a single multiplication. So let's think of this. You are doing inner product of two vectors. Let's just think of multiplying two values for now. So you essentially have an encoding of K. So you have A1 plus K times G and A2 plus C times G. And essentially we're trying to get to something plus K times C times G. All right. And turns out the way you handle multiplication gates in the BGG plus ABE schemes has a very nice property that when you combine these values, you only need to know, whenever you have a multiplication gate, you only need to know one of the two wires coming into the multiplication gate. Okay. So this allows, so you only need to know either C or K, and you can arrange it so that you only know C and don't need to know K. All right. And here, this is exactly the scenario that we have. We're doing a multiplication. On the left wire is the secret key. On the right wire is the ciphertext. The ciphertext you know, so you can arrange it so that you do a multiplication gate only knowing one of the two wires. Right? So then that gives you correctness.
And in addition, you don't need to know either.
Addition doesn't matter. Yeah, you don't need to know either. Okay. Are there any questions? So we're really exploiting properties of the AB scheme. Sorry?
Why is it obvious that you never have to deal with two bits of the private key?
So you do each of the multiplications bitwise. Addition is completely oblivious to the wire values.
Specifically inner product.
Completely inner product. Right, yeah. So you do... Okay. Any questions? Okay. Great. So just to summarize the scheme, here's what the ciphertext looks like. All right. Your secret key is going to be basically creating some sort of ABE secret key that sort of checks. You want to be able to decrypt if the decryption of the inner product is close to zero. Basically, that corresponds to a FHE encryption of zero. Right? So one thing I didn't say is that in FHE decryption, it's not only computing an inner product. You have to do inner product with rounding. So you're not checking whether, you don't decrypt when the inner product is exactly zero, but you need to be able to decrypt when the inner product lies in some small interval. Okay? So for our purpose, it's extremely important that this interval has size polynomial in the security parameter. All right? And this is something that's achieved in the Brackerski, Vakuntanath, FHE. And then once you know that the inner product lies within a certain interval, you basically give out many ABE secret keys correspond to each of these values in the interval.
So for polynomial size range, you just need modulus chain, modulus suppression.
You can get it from probably.
So you don't actually need
Okay.
There was already in Gentry's scheme, there was also a way to get it to polynomial.
Okay, so anyway, you just need polynomial noise for sure. Maybe there are prior schemes that already achieve it. You need the noise of the evaluated ciphertext to fall within a polynomial size interval, because you're going to give out one secret key for each of the points in this interval. So the final secret keys are many ABE secret keys.
So you have a general theorem. If your ABE scheme has this kind of decryption property, like the inner product, then you can.
Yes.
You could write it as a general theorem.
Right. Yeah. So in the paper we do present it that way. You have to be a bit careful. You need to have a setting where you can operate arbitrary computation on some public part, and then the private part you only do an inner product.
Yeah. But I mean, inner product doesn't exist. An ABE where inner product can be supported.
Right. Yeah. Yeah. In the oblivious way, and both security and correctness. Yes. So I wanted to. I'm not going to have time for the proof, but let me just quickly say that the proof essentially uses the fact that in, like Luca pointed out, in existing ABE schemes, they basically have this property that the ciphertext looks like an encryption of the attribute, and that essentially allows you to hide the attribute. Right? So we essentially need to only hide the FHE secret key.
And you had selective security.
Right, we only get selective security like before. So the proof is not too hard. You can do the whole thing. All right. So going back to the question that everyone has, so what does this tell us about functional encryption for all circuits? Right, so as Shafi said, so what we present essentially, or as Benny said also, what essentially show is sort of a bootstrapping type theorem that is sufficient sort of to do functional encryption for FHE decryption in some sense, which corresponds to just doing inner product with rounding. All right. So essentially, if you manage to build a functional encryption scheme for this simple functionality of inner product with rounding, so you already know how to do it without rounding. If you can do it for inner product with rounding, then you get functional encryption for all circuits. Okay. Moreover, the construction has the property that your ciphertext is very short, so it satisfies this compactness requirement, and this via recent works will in fact also give you obfuscation for circuits. So really what we show is in some sense that really it's just sufficient to just build functional encryption for a very, very simple function. This is a meta theorem, not an exact precise statement, because we need special properties from, we do exploit certain algebraic properties of the underlying scheme. All right, so to conclude, let me conclude on a slightly personal note. So I started working on functional encryption like around 2010 when functional encryption was trending. So this is a time when, I had no grants, I had no tenure, nothing, And then I decided to start working on functional encryption, sort of for the wrong reason. Because it appeared to me that functional encryption was crypto complete. Maybe I'll be able to get more papers, I can get grants, I can get tenure. Right? 5 years later, it's not quite trending anymore. It's sort of going down, and yet I'm still working on functional encryption, and my motivation has changed. Now I work on functional encryption because functional encryption is crypto complete. In particular, it implies that this is proof via reduction to obfuscation. We all think that obfuscation is crypto complete. Functional encryption implies obfuscation, so functional encryption is crypto complete. In fact, there's some sense in which the techniques developed in the context of functional encryption has already had a huge impact on cryptography outside of functional encryption itself. So today we have seen connections to fully homomorphic encryption, fully homomorphic signatures. One thing none of us talked about today are sort of using techniques from functional encryption to give you delegation, signatures, CCA, NISIC, so on and so forth. Okay? So, right. So I hope somehow our talks have sort of motivated some of you to start thinking and working on functional encryption, and I look forward to the next 5 years of functional encryption. Thank you.
So we know, the question to both of you, so we not alluded to a deep connection to these techniques on FHE and fully homomorphic signatures, and indeed, for example, the way you compute the public key But the functionalities are different. So Netryk is basically actually get the message, not just encryption. So is there kind of a clear connection to just syntactic coincidence, or there is something?
No, there's no connection. So Daniel and Zvika talked about the connection between homomorphic signatures and homomorphic encryption. Right? They're really the same thing, except we switch parameters. So here's the way to look at it. So there's one is connection between signatures and IP. Right? From any IP, you can pull out a signature. The question is, can you go back? Right? Can you take a signature and can you tack on something else on top of it to get an IP? So you could sort of think about this question. You could sort of upgrade this question a little bit. Right? You could say, suppose I had a homomorphic signature, right? And I tack on an encryption on top of it, just the way you would take a signature and tack on an encryption to get an IP. What would you get? Turns out you get exactly AP. The AP that I was
saying if you take on fully homomorphic encryption
signatures.
But if you have fully homomorphic signatures and you tag in what?
An encryption, a way to encrypt with
No.
It's not a generic statement. It's a
That's it.
fairly specific statement.
You take an ABE downgrade.
From A to B, you get C.
But the signatures buy you the non-malleability property, so it helps you protect against collusions. But the next hard part is to protect the attribute, and that's something that doesn't seem to come from any sort of signature guarantees.
I was just saying, so you said from A plus B you get C. So I understand A is fully homomorphic signatures. What is B and C? One of them is attribute-based encryption. So can you clarify what
C
is
is attribute-based encryption, but I'm not claiming a generic statement.
What is B? Then what is B?
No, I'm not claiming a generic statement, so I don't know what to say what B is. But there's a clearer picture in the homomorphic signatures versus encryption. Not so much in ABE, but there's still.
It's a technique. If you had an encryption scheme that does blah, then you.
And the blah is a pretty simple blah.
But it's worth noting that the signatures in the fully homomorphic signature scheme are not the secret keys in the ABE scheme. They are the simulated secret keys in the ABE scheme used in the proof of security. So the scheme corresponds to proof of security, which is different from Money's transformation for signatures, where the signing algorithm is the key generation algorithm. In the fully homomorphic signatures, the signing algorithm is the simulated key generation algorithm used in the proof of security, not the honest key generation algorithm.
No, that's
statement.
clear.
Yeah, so certainly a lot more delicate.